EET 114, Chapter 26, Non-Sinusoidal Circuits. So, what is a non-sinusoid? Well, here's examples. Okay, straight line, a DC voltage in this case is non-sinusoidal. A pulse wave, non-sinusoidal triangular wave. We have like we call a sawtooth. And then this is a rectified wave. What does rectified mean? Well, basically, this is a half wave rectifier, meaning it only gets half of the waves. Um, in this case, it would be the top half, the positive going half. um, if you put a diode in here, and we never talked about what a diode is, but it only allows current to flow in one direction. Okay. And the direction's indicated by the diode. So it allows current flow in this direction, but when it goes to flow back, it just doesn't allow it. It stops it. That's what this bar is, this line, this vertical line. So anyways, when you look at the current coming in and the current coming out, the current in looks like a regular sinusoid and the current out looks like this, which is a half wave rectified, okay? So it's only allowing the positive to go through here. When it goes in this direction, it allows it to go through. When it goes back the other way, it doesn't allow any current flow and it's just flat. So it's clipped. Um, so those are examples of what they look like. The first thing we're going to talk about is a Fourier series, section 2. Very, very important. This is the average value. Okay, this is the general equation for a Fourier series. The first term is the DC or average value. Now, why is it called that? Because it's not a sinusoid. It is just a constant. It's going to be a constant number. It doesn't have to be an integer, but it's going to be some kind of number. And then each successive term is going to be a sinusoid. Notice that the first term has an amplitude A1 and then a frequency of omega. That's the radial velocity, which is still 2 pi f. And then the second term has a multiplier of that frequency. So it's double the frequency and it has a different amplitude and so on and so forth. This is 3 times omega here. And then it goes on and on until you get to n, whatever n is. N could be 2, 3, 12, whatever it is. It's how many terms are in sine terms are in the circuit. And then there could also be cosine terms, okay, and they follow the same pattern. Now this is a simplified way to draw it, and to write it out. It's writing out omega is 2 pi f. In the case of this particular equation, it's f sub 0. What is f0? F0 is the fundamental frequency. So it's the frequency on which all these other sinusoids ride. So when you add these together, you definitely get a non-sinusoidal circuit. It's going to look like a bunch of noise. All right, you're going to have this fundamental frequency f0, this sine, and then when you add these other sines and cosines to it, it's going to be a non-sinusoid for sure. The Fourier spectrum. Once the frequency components of a non-sinusoidal waveform have been determined, the waveform can be defined by the magnitude of the harmonics and their associated frequencies rather than against time as appearing in all the previous chapters. Okay, so what does that mean? Well, here's a non-sinusoidal square wave, okay, and it's plotted versus time. You can break this signal down into a plot of voltage. This is voltage versus time. You could break it down into voltage versus frequency, okay? So you have these little spikes on here, okay, these impulses. And whenever you have this broken down, this is what it looks like, okay? This is the equation. So this is 8 plus 10.19 sine of 2 pi f0, 3.40 sine of 2 pi. So what does that mean? Okay, the frequency here is f0, and that's this plot, and then the magnitude is 10.19. So that's how you represent it. The first DC term, the average value or DC value, is right here, and it's on frequency of 0 because it doesn't have a sinusoid. And then 3f0, in this case, the magnitude is 3.4, and then so on. 5f0, the magnitude is 2.04, and you can see how this moves on. These are called odd harmonics. Odd because they have an odd multiplier, the odd numbers 1, 3, 5, 7, 9. The even harmonics aren't as interesting. They're going to be the 2, 4, 6, 8, 10. So we're going to continue talking about this. The Fourier spectrum, which is what this thing is, appears over here. Note on the Fourier spectrum, the value of the function of 8 volt is at frequency 0. That's the DC value corresponding with the DC level. And the fundamental frequency, first harmonic of 5 kilohertz, because we were given here that the frequency is 5 kilohertz and the period is 0.2 milliseconds. So the first harmonic of 5 kilohertz, the peak value of the contribution is 10.19. For the next harmonic, this is would be called the third harmonic, 15 kilohertz. That's the frequency. The peak value is 3.40. So for the fifth harmonic, 25 kilohertz, peak value is 2.04. And F0, 5F0 drops to 1.46, 7F0, 1.13. Note how quickly the terms drop and increase with frequency. That's very typical. You're going to see this kind of situation where, even in pure um, the power that's in your wall has harmonics in it. Okay, it's not just 60 hertz. There's going to be other, you know, like if the fundamental frequency of the power of your wall is 60, this would be 180. This is going to be 300. This is going to be 420 hertz. There is some contribution. There is a magnitude of any even though these might be small, they're still going to be there. If they get big enough, they can be a problem in the power grid, and they might need to be cleaned out. Especially if you're in a factory setting or you're in a laboratory setting where you have sensitive equipment. You don't want these frequencies to invade your measurements or whatever you're trying to do with the power. So here's another example below. This is a 12 volt DC source, 0 volts, 0 hertz, 12 volt DC. So for a single DC source, 12V, the Fourier spectrum would appear as shown. And for a sine wave with a peak of 6 volts and a frequency of 500 kilohertz, this is how it would appear. So these are a simple example, okay? This would be just a DC source, and this is what it would look like graphically. And then this is the graph, the Fourier spectrum of just this frequency.